Hi everyone, welcome back. So now we have just been talking about stars, and one of the really cool things about what we know about stars is based upon our nearest and dearest star to us, which is the sun. So the sun is obviously a star, and one of the benefits that we get from the sun is that it's not just essentially a pinprick in the sky of light, that we can actually observe and resolve a lot of features on the sun and learn a lot about the sun. So what we know about stars influences what we know about the sun, but similarly, what we know about the sun also influences what we know about stars as well.
Yeah, absolutely. And that's a really important point that we can resolve the sun's surface. We can see all the different bits and where things are happening and where they aren't, and see little features on it that we don't see in other stars. There's only something like 10 other stars we can measure their surfaces in more than just a single point. And even those, it's not anywhere near the sun. The sun is really, really close to us. And so we get really beautiful data for it. And yeah, we can use one to understand the other. Looking at the sun, we have a couple hundred years of data using telescopes, back to about 400 years. So anything that happens 1 in 1,000 years, we don't really see. We can use stars that are very like the sun to understand how often those rare events can happen. And similarly, we can use the really, really detailed information we have for the sun to better use stellar models. That we don't have to worry about when we test our models. We know really well the sun's parameters. It's a 1 solar mass, 1 solar radius star, and so our models of 1 solar mass, 1 solar radius stars have to match the sun, and so those are really, really precise. And as we get further and further away from the sun, things get a little harder.
Yeah, and we can learn a lot about the sun and other stars, not just from what we see on the surface, but what we can't see of what's happening around the sun as well.
Yeah, and a lot of that is driven by the sun's magnetic field. We've talked a lot about stellar structure in this course, and convective zones and radiative zones, things like that. Those are things we all understand really well. Magnetic fields are really an active research in the sun, that they drive a lot of important things. Things like star spots and flares, which we'll talk about in a couple minutes here. And they affect rotation and the way rotation changes over time. But we don't really understand them. It's a really, people who really study stars as stellar physics, a lot of what they do is study magnetic fields right now.
Yeah, and it's funny because you can do a lot of studies of stars and a lot of theoretical models of stars completely ignoring magnetic fields. A lot of the way that stars evolve, you can ignore magnetic fields, but when we're talking about the really precise, more precise measurements of stars and things that are happening on the surface, yeah, the magnetic fields become super, super important.
Right, and a lot of times now we really care about precise things. When we're talking about finding Earth-sized planets, those signals are parts per million, not a few percent. And so yeah, you can get the 10%, 5% level in most cases, completely ignoring magnetic fields. But when you care about the 1% to get down to, is this Earth-like planet I've discovered actually Earth-like in any meaningful way, turns out magnetic fields become really important. And so now it's something we care about deeply.
And on the surface of the sun, we can, obviously, we can't see the sun's magnetic field, but we can see the way that it, the way that it manifests on the surface. And there are lots of, we can obviously, get instrumentation to measure magnetic fields and such, but we can see what's happening on the surface because of the sun's magnetic field. And a couple of these features are things like sunspots and solar flares.
Yeah, absolutely. And sunspots, you can look at photos of the sun and see them and not be that impressed of, oh, there's a sunspot there. But really, it's important to remember how big the sun is. It's about 100 times the radius of the Earth. And so when you're looking at these photos of sunspots, these things are many times the size of the Earth. When you get those arches that are on the sun's surface, those are bigger than the Earth. These are really, really dramatic features.
Yeah, and you might think, oh, that's a bit boring. It's just a black spot on the sun, but these tell us so much about the physics that's happening, and what's happening inside the sun, and the way that the magnetic field interacts, in and out of the surface, and with solar flares, the way it actually ejects material from the surface. This is all really important that we study these things in great detail.
Yeah, and there's a couple of really exciting things we can learn about sunspots. And there's a few different features on the surface. Sunspots are these dark regions on the star. Faculae or plages are the bright regions. They're both magnetic in nature, and they're both usually playing off the same magnetic field, that you'll have a dark star spot surrounded by a bright facula, images you can see here. They're also very dramatic at certain wavelengths. The magnetic fields really affect ultraviolet observations. And so when you look at the star in the infrared or with your own eyes in the optical, star spots don't look that dramatic. When you look at the UV, it's much more exciting, very, very dramatic star spots, and the faculae really jump out. You can see those as you look at different wavelengths here. But let's get back to the exciting things, which are what we can use star spots to understand for the sun. First obvious thing is the rotation period. That the sun, like everything else in the solar system, is rotating. And star spots give us a marker on the star, on the sun, to see what surface we're looking at. It's not this totally uniform, homogeneous ball. The sun is rotating, and the star spots are rotating with it. And so we can see, based off of every day you watch the star spot come and go, go across the surface, how long does it take for the star to rotate fully around? And for the sun, that's about 25 days. For different stars, this could be very different. It's a function of age, it turns out. Younger stars rotate very quickly, and they lose momentum in time. They slow down. And we understand this in very much the same way of looking at sunspots, or star spots on other stars, we call them. Because the star spot is a dark spot. We don't resolve the actual spot to see it. But because it's a dark spot, it's blocking some of the star's light, so the star's a little fainter in time. And so as we watch the star go through a rotation, the star appears brighter and fainter and brighter and fainter, and so we can use that to map out what its period is. The sun is pretty typical for a 4.5 billion-year-old star at 25 days, but it's a function of mass and age. Lots of young stars rotate with a period of a day or two. So that's the first thing that we're really excited about. Second thing is looking at longer cycles. Star spots are not constant. They come and go in time, and they also change latitude in time. That's over the several years, we see star spots form at one latitude, and then they start changing in latitude. They occur at different ones, and then we spend a few years where there's a whole bunch of star spots, and then they kind of go away for a few years, and then start getting a bunch more star spots.
Yeah, and if you're ever fortunate enough to actually do some solar observing when the sun's surface is really active, it's really quite magnificent. So if that opportunity comes up, we would definitely recommend doing it.
Yeah, there are some beautiful figures you can find too of this changing in time, which is people have plotted locations of star spots by year, and it's called a butterfly diagram because it kind of looks like a butterfly. You see these two wings spread out as the star spots go from high latitudes to low latitudes. They get closer together on both hemispheres, and then they kind of decay, and then a new butterfly starts. It's beautiful. It's gorgeous data. There's 400 years of it, going back to Galileo. And so what we've seen is that the sun has this 11-year cycle of more spots and fewer spots, and other stars have very similar cycles. This is also a function of age and mass. But it's the sun's 11-year cycle. It's magnetic in nature. We don't really understand where it comes from. This is a very active field to understand what these fields look like. No pun intended. But
pun intended.
Understanding the sun has an 11-year cycle. We're trying very hard to work it out, and we use data from the sun and also from other stars to understand, the suns, we can understand the magnetic cycle in much more detail than anyone else's, than any other star. And all these other stars help contextualize it to see how is it different as a function of the star's mass, the star's composition, and things like that. And it has lots of effects for us on Earth, too. We don't always notice it, but birds navigate through magnetism. Whales travel through magnetism as well. They help orient themselves. And there's actually studies that have shown that there's a correlation that over 11 years, the number of whale beachings, whales getting stuck on beaches, changes. That at certain points in the magnetic cycle, whales struggle to navigate and are more likely to get beached. And so they're certainly affected by the magnetic cycle.
Yeah, you might just think that the only solar activity that kind of affects us on Earth are those really coronal mass ejections or something like this that really throws a lot of material our way from the sun, and then that obviously plays havoc with communication and stuff like that. But yeah, just on a general, like even when the sun's just doing its normal thing and not ejecting material our way, that it still affects life on Earth as well.
Yeah, and when it is ejecting material, it's the risks to communications. There's also, you can notice it through aurorae if you're at high latitudes. That those happen more often in the high activity parts of the 11-year cycle. So there's been many aurorae over the past couple of years, and that will start to fade away as we leave the high magnetic cycle, go to the low one, and then cycle back a decade from now.
Awesome.
Yeah.
So we hope you enjoyed learning more about the sun and the fact that the sun is a star, and we will see you in the next video.